Okay, so hi, my name is Robert. I'm here to present the paper, De-randomizing Matrix Concentration Inequalities from Free Probability. This is joint work with my advisor, Lapchi Lau and Hongzhou. Okay, so matrix concentration inequalities are probabilistic bounds on the eigenvalues of random matrices. These are fundamental and very useful tools in probability theory. And for today's talk, we will focus on the self-adjoint random matrix X with expectation 0. And we want to study concentration inequalities that bound its maximum eigenvalue or spectral norm. Our paper actually does more than this, but just for simplicity, we'll just focus on this model today. Okay, so a recent, very exciting line of works has developed a new set of matrix concentration inequalities using ideas from free probability. And in particular, these concentration inequalities are very sharp on a very broad class of random matrices. And this has led to some new interesting applications in computer science, including a new breakthrough in the matrix Spencer conjecture, as well as new constructions of near-Ramanujan graphs. So in this work, our goal is to de-randomize these concentration inequalities by deterministically constructing matrices in polynomial time that satisfy their bounds. And as a consequence, we also de-randomize many of the new algorithmic applications of these bounds. So I'll start by introducing the Gaussian matrix model, which is when the matrix X has jointly Gaussian entries. So for these matrices, we can write them as X equals summation I GIAI, where the GIs are IID independent Gaussians, and the AIs are symmetric d by d coefficient matrices. So the classical non-commutative Khinchin inequality says that the expected norm of X is bounded between sigma X and sigma X times root log n, where this sigma X is called the matrix variance parameter, and it is the norm of the sum of the squared coefficient matrices. In the scalar setting, this is just the variance of a Gaussian. So both the upper and lower bound of this inequality can be tight depending on the example. And a fundamental question in random matrix theory is trying to understand when is the lower bound tight. In other words, when can we remove this root log factor from the upper bound? So to sort of address this question, recent work by Bandera, Bodiharjo, and Van Handel proved a new set of strong matrix concentration inequalities based on a new matrix parameter called the intrinsic freeness parameter. So to explain this, we define the quantity nu x squared to be the maximum eigenvalue of the d squared by t squared covariance matrix of the entries of X. You can also think of this matrix as just the sum of the outer products of the vectorizations of these coefficient matrices. So in other words, we treat X as just a one giant vector, and we take this covariance matrix. And what they showed is that in the Gaussian setting, the expected norm is upper bounded by 2 sigma x plus the geometric mean between sigma x and this new nu x parameter times some polylog factor. And in particular, if nu x is much less than sigma x, this red part becomes negligible, and the bound is just dominated by 2 sigma x, in which case the lower bound part of Khinchin would be tight. And these matrices, we refer to them as intrinsically free. So to just give some examples to illustrate these bounds, consider the simple case where X has independent entries, and we normalize the matrix variance sigma X to be equal to 1. In this case, we can verify that the nu x squared parameter is always going to be roughly the maximum variance of any entry. And okay, so in the first example on the left, consider when X is a diagonal matrix. In this case, its norm is just the maximum diagonal entry, and the expectation of this quantity is just root log d, which means that the upper bound of Khinchin is tight. So in other words, no improvement can be made. And indeed, we see that because every row, the variance is all concentrated on the diagonal entry, the nu x parameter is also equal to 1. So X is not intrinsically free. On the other example, we have a case where all entries of X are Gaussian with the same variance, and these are called Wigner matrices, and they're very well studied, and it is known that the norm of X in this case concentrates around 2. And indeed, because the variance is very well spread over the entries, the new x parameter is on the order of 1 over root d, which is much smaller than sigma. So x is intrinsically free, and in fact, this BBVH inequality actually correctly predicts the norm of x up to the leading constant factor of 2. So you can see that it is very sharp in a lot of settings. Okay, so beyond just Gaussian matrices, we may also consider what about general non-Gaussian matrices. So we may consider the sum of independent random matrix model, where X is the sum of a bunch of arbitrary independent matrices Zi with zero mean and bounded norm. And we define the parameter rho X to be the maximum norm of any of the Zi's. And there's this thing called the universality principle, which states that if rho X is small, then this matrix X roughly behaves like a Gaussian matrix with the same mean and covariance profile. So you can interpret this as sort of a matrix version of the CLT principle. Right? So again, the Zi's do not need to be Gaussian, they can be any kind of random matrix. So the classical matrix Bernstein inequality says that the expected norm of x is upper bounded by sigma x times root log d plus this rho x times log d factor, which, as you can see, if rho x is much less than sigma x, this part becomes negligible, and the bound just reduces to the Gaussian Khinchin inequality. So in a recent work by Briolis-Kaya and Van Handel, they essentially extended the bounds of BBVH to this general universality setting, and they showed that the expected norm of x is upper bounded by 2 sigma x plus this intrinsic freeness parameter in the red, which is from BBVH, and then plus another sort of error term that is also vanishingly small as long as rho is much less than sigma. So again, there's a lot of quantities here, but as long as nu x and sigma x, and rho x are much less than the matrix variance, then the norm is essentially upper bounded by 2 sigma. So the general universality model is quite powerful. It can be used to represent a lot of different models. And a classical result of Witgerson and Xiao actually de-randomized this matrix Bernstein type inequalities for this model in order to give deterministic algorithms for constructing expander graphs and rounding STPs in polynomial time. So our work, in some sense, is an analog of Wigderson and Xiao, but for the new matrix concentration inequalities based on intrinsic freeness. So now I will state some of our results. So our first result is a de-randomization of the Gaussian concentration inequalities. So given a set of symmetric coefficient matrices A1 up to AN, we deterministically compute a vector x of length root n, such that the norm of summation I ai xi is upper bounded by 2 sigma plus the intrinsic freeness parameter, as in the BBVH bound. Moreover, we can extend this by, in addition, requiring x to satisfy omega n linear constraints at the cost of an extra constant factor loss on the right-hand side. So our second result is a de-randomization of the universality principle. So we're given this general random matrix model, X, which is the sum of independent Zi's with a zero mean. And we also assume that each Zi has polynomial support size. So each Zi is simple enough that you can enumerate across all of its possible outcomes. And we show that we can compute in polynomial time matrix Z in the support of X, whose norm is upper bounded by 2 sigma plus this intrinsic freeness parameter plus this universality parameter. So to give some applications of our work, I'll go through 2 interesting ones in the paper. So our first application is a de-randomization of the low-rank matrix Spencer problem, which uses our Gaussian concentration inequality. So given a set of coefficient matrices A1 up to AN, the matrix Spencer conjecture asks if there exists a plus minus 1 signing X such that the norm of summation I ai xi, or the discrepancy of X, is small, in particular upper bounded by O of root n. And through a standard reduction, it actually suffices to find a low discrepancy partial coloring, which is a vector X whose entries are between -1 and 1, but at least a constant fraction of them is in plus minus 1. And recently, in a breakthrough result by Bansao, Jiang, and Mecca, it was shown that you can resolve the matrix Spencer conjecture when each input matrix has rank at most n over polylog n through a randomized algorithm. And the main observation in that paper is that under the low rank assumption, you can project all of your input coefficient matrices onto a subspace of dimension at least constant in n. And this will, and in the subspace, the matrix is intrinsically free. And this essentially allows you to obtain a good partial coloring by applying a standard geometric projection algorithm. So what we do is that we de-randomize, by de-randomizing the Gaussian concentration inequality, we can make this projection step deterministic and thereby resolving, deterministically finding a partial coloring in polynomial time. Our second application is in the construction of near Ramanujan graphs, which uses our deterministic universality result. So basically, a Ramanujan graph is basically an expander with optimal spectral gap. An expander, so given a k-regular graph, we say that this, basically a Ramanujan graph is a graph where the second largest eigenvalue in magnitude of its adjacency matrix is upper bounded by 2 root k minus 1. Right? And asymptotically, they are the best possible expanders. And a classic result of Friedman is that if you sample a uniform random k-regular graph over n vertices, as n grows, this graph becomes near Ramanujan with high probability. In particular, its second eigenvalue converges towards the 2 root k minus 1 in probability. And later on, Brelos-Kaya and Van Handel showed as a consequence of their matrix concentration inequality that this phenomenon continues to hold when the degree k is allowed to grow with n. So in particular, they showed that you can construct near Ramanujan graphs of degree at least polylogarithmic in n. So by de-randomizing their result, we give the first polynomial time deterministic constructions of near Ramanujan graphs in this moderately high degree regime where k is at least polylogarithmic in n. Okay, so for the remaining talk, I'll just briefly overview the general principles behind these concentration inequalities. So the general idea behind these new concentration inequalities is to compare the eigenvalues of a random matrix with those of a certain infinite dimensional operator from free probability, which we call x free. And in particular, this operator is constructed by taking the Gaussian variables in X and replacing them with a family of deterministic infinite dimensional operators called free semicircular operators. If unfamiliar, you can think of these as essentially an infinite dimensional representation of very, very large Wigner matrices with unit variance and dimension tending towards infinity. So in some sense, you can treat X-free as a really, really big random matrix where we replace each Gaussian with a big Wigner matrix. And the nice thing about X-free is that because it's deterministic and we can use some nice results from free probability to study it, we know that its norm can be computed exactly in polynomial time. And we can also, whenever X is intrinsically free, essentially what they show is that the spectral statistics of X and X3 are close to each other. In particular, the expected norm is close to the norm of X3. And we also know, using basic results from free probability, that the norm of X3 is upper bounded by 2 sigma x. And this gives us this sharp bound in the norm of the random matrix. So the general idea behind our de-randomization of these bounds is to sort of use kind of a variant of the method of conditional expectation. So in the method of conditional expectations, we want to iteratively sample values for our random variables while maintaining a good bound on the expected value of some objective function conditioned on what we've sampled so far. And okay, so we can try to apply the method of conditional expectation to the trace moments of X. A standard fact is that if you take the pth trace moment of X, where p is on the order of log d, and then take the normalization 1 over power 1 over 2p, then this sort of Schatten moment norm is a constant factor approximation for the expected norm of X, expected maximum eigenvalue. But the problem with trying to apply the method of conditional expectation on this is that we don't really know how to compute the expected trace moments of a general random matrix. But because when X is intrinsically free, the expected trace norms of X are close to the trace moments of the infinite dimensional operator X free, we can use these quantities as a proxy for the conditional expectation in our algorithm. And again, these trace moments of X free can be computed polynomial time deterministically using basic identities from free probability. So, right, and then as a result, we're able to output a random matrix whose eigenvalues are close to those of X free. As a final remark, we note that in implementing our ideas, we also ended up finding new algorithmic proofs of the matrix concentration inequalities from BBVH and BVH in all of these models. And it's nice because our algorithm now uses techniques from theoretical computer science, including the barrier method, which was previously used for spectral specification, and this Brownian walk algorithm from discrepancy theory that Nikhil talked about earlier. Yeah, so some open questions that still remains is whether we can, for example, improve our construction of expanders. So recently, it was shown that actually uniform random regular graphs are truly Ramanujan with constant probability, which means the eigenvalue is exactly less than 2 root k minus 1. So the question is, can we also de-randomize this kind of result? Another interesting question is, can we find a construction of near Ramanujan graphs that includes all degree regimes, from the constant degree regime all the way up to, like logarithmic or super logarithmic, or yeah, so covers all the regimes. Yeah, and yeah, so so I mean, there's a lot more to the paper, so that I didn't get time to go through. So yeah, feel free to ask any questions. Yeah.
So is there any hope of using some of this machinery to also de-randomize via some small sample space? Like that trace moment argument, you can kind of de-randomize using piecewise independence.
Yeah. So in fact, okay, I took this slide out of the presentation because of time, but essentially, roughly what we do is that we do a step-by-step analysis where we sort of replace a little bit of the Gaussian, a little bit of the semicircular stuff with a Gaussian at a time, and this Gaussian we can replace with a pairwise independent vector, which can so each step can be de-randomized in polynomial time. Yeah, it will be interesting to see if using higher order independence could improve these kind of results. Yeah.